Hi there! Today I'm going to give a quick introduction about the topic of stability and demonstrate a program I have written to do such. So what is stability? Stability is when we apply perturbations to state variables in a system and the change relaxes back to the original state. We call this system a stable system. So an important example is biochemical pathways. If a biochemical pathway is dynamically stable at steady state, this means small perturbations in the floating species concentrations relax back to the original state. Another really important idea of stability in the real world is biological organisms. They are continuously subjected to perturbations. These perturbations can originate from external influences such as changes in temperature, light, or nutrients. Perturbations can also arise internally due to nature of molecular events or by genetic variation. One of the most remarkable and characteristic properties of living systems is their ability to resist such perturbations and maintain steady internal conditions. So just a quick example, a graphical visual understanding. Here we're taking a two-step pathway, and once the system evolves to steady state, at 0.5 here, we're applying this perturbation in x1, and we see that it relaxes back to this original steady state. So this is what I mean by relaxing back to steady state. We can also explain the difference between internal and external steady state. So internal is the tendency for the system to return to steady state after one or more of the state variables have been perturbed, whereas external is a finite change to an input of the system. That will give a finite change to the steady state overall of that system. So we have three main ways we can determine stability now that we understand the concept. So I'm just going to go ahead and run through these. The first would be to apply a perturbation in our differential equation, right? So we can write a differential equation about the change of species over time. And so we can change this x value, we're looking at our species x, we'll perturb it by changing this to x plus delta x here. We're going to use that. And if we plug in our steady state value as well, some terms cancel out, and we will end up with this equation. We can see that the derivative here is negative. So in other words, the rate of change of the disturbance x is negative, so the system attempts to reduce the disturbance so that the system returns back to the original steady state. So if the rate of change of x had been positive instead, the perturbation would have continued to diverge away from the original steady state, and we consider this an unstable system. A second way to calculate it is through poles. So a transfer function is the response to a system when the input is an impulse function in the Laplace domain. So you can see this form that our transfer function is given in here. The denominator of this is the characteristic polynomial, and if we set this equal to 0, it will give us the characteristic equation. And then the roots of these characteristic equation are called the poles. And if we put this back into the time domain, we will get a sum of exponential equation here, and these exponents will tell us the stability. So if all these poles are negative, meaning these exponents are negative, the system is stable. And the third way is related to the last way we discussed. You can take the Jacobian matrix. So if you take the derivative of the first differential equation you have, this is good for larger systems. Take the derivative of the first differential equation you have with respect to the first variable, and then that equation with the second variable, and so on. And then you would do this for all equations and all variables, and you get this Jacobian matrix. The solution to this is also a sum of exponentials, as we saw before. So the exponents are the eigenvalues. If you calculate the eigenvalues of this Jacobian matrix and all the eigenvalues are negative, you will determine that it's stable. If they're not, it will be an unstable system. So here's a quick chart of behavior of different systems. You don't have to focus too much on that right now. We'll go into more depth later. But basically we can represent these different eigenvalues, have real and imaginary components. If the reals are greater than 0, less than, etc., it means different things, as well as if they're complex. So we'll just run through some of these. One thing to understand is the phase space. So that's where all possible states are represented. So we'll look at different trajectories of our species. And it's really nice if we have a two variable system. We can look at x and x1 and x2 on an x and y plot, plotting them against each other. If we also plot the eigenvalues, we can get an argand plot, which will show the real and imaginary components. So these are the 6 main phase plots that you can get, but I'll go ahead and run through my code and we can really determine those. Great, so here you'll see my code. Just run through it really quick. So we're going to obtain user input for that Jacobian matrix we just talked about. So user could input any values for the A, B, C, D components of a 2x2 matrix. Then we're going to calculate the eigenvalues of that matrix, and we'll print those out to the user just so they know what those values are. Then we're going to go ahead and create our argand plot. So I'm going to separate these eigenvalues into their real and imaginary components here, and I'm going to plot real versus imaginary on this plot here. The next thing we're going to do is take those eigenvalues, and I showed you that table before to determine the stability. So this is just a bunch of if statements that will report out to the user if it's unstable, stable, what type of phase plot we're going to get. This is where those values they entered will come into this matrix. So we're just creating a matrix here of the differential equations. And then we're going to give it a time range. And here I have 2 for loops. These for loops are changing our initial conditions of both x's every time we loop through this. So we're going to get a lot of different initial conditions. We're going to basically solve those 2 differential equations, and then we're going to plot those 2 solutions against each other. And then I'm also going to take those same solutions and plot them against time as well, but I can give those their own independent time range and initial conditions to kind of see what happens. So let's just go ahead and run a quick test of this code. So here it's prompting the user to enter your Jacobian matrix values. So we'll give it -2, 0, -0.15, and -2. I'm just going to display a few different systems. So here it tells me the eigenvalues are -2, -2, and it's predicting to be stable. So looking at these plots that we get, this is the argand plot. So we see real versus imaginary, and this makes sense. We saw we had -2, -2, so they're both plotting at this same -2 spot, and they're real, so we don't have any in this imaginary direction here. And then if we pull up the other plot that we got, we see we have my x1 and x2 trajectories over time. These are converging. I gave them 10 and 10 initial conditions. They're converging towards 0 over time, which does display a stable system. And then here we see the phase plot, and the trajectories of x1 plotted here and x2 here are also, we see these arrows, these are all different trajectories, converging to this 0 center point. So let's go ahead and run this for another system. So I'm going to go ahead and enter 1.2, -2, -0.05, and 1.35. So we're getting the eigenvalues here. Again, they're real. We'll notice that they're both positive this time, as they were both negative last time. And then it's predicting it to be an unstable system. So let's look at these plots. Great. So what we see here is that we had both positive real values this time. Again, nothing in that imaginary area. And then if we look at our second figure, we do see that this was unstable, right? So this started at these initial conditions of 10 and just really took off, diverging away from 0, just really exponentially growing there. And then here in the phase plot, we see these trajectories. All of our arrows from our initial conditions are diverging away from that 0 center point again. So I'm just going to give you a feel for 1 or 2 more systems before I run out of time. We're going to run it again. We'll do 2, -1, 1, -2, and we'll see here, so we have a positive and negative eigenvalue. That's going to give us this saddle point plot. So once again, we don't have any imaginary components. We see it's all on this real axis. 1 is positive eigenvalue, 1 is a negative eigenvalue. Then we'll take a look here, and we see we do have this saddle point. So if we were to remain on this diagonal, see these arrows are pointing towards the center if you remain on either of these diagonals, but as soon, or this diagonal here, but as soon as you start a trajectory away from there, you're just going to really diverge away. And then we see that this is somewhat unstable as it's diverging away from the initial conditions as well. All right, I just want to do one more to give you a taste of complex as well. I know I'm running out of time here, but we'll just do one more user input. 1, -1. So we see we get these imaginary components in our eigenvalues. We have 2 negative reals, and then we have these imaginary components that are complex conjugates. And we're going to get a stable spiral. Now, if these reals had been positive, we'd get an unstable spiral. I don't think I have time to show that. So this is what an argand plot will look like if we have a complex eigenvalues. So you see now we have it on this real component, and we have it in this imaginary component here, okay? And they were both negative in this case. You can also get both positive in the real. In the real, you're always going to have positive and negative imaginary values for those conjugates. And then we'll take a look here, and we did say we were going to get a stable spiral. So we see that it is converging towards this center 0 here. And then these initial conditions really, we get an oscillatory motion. We begin to get that in these complex values. But we're starting at these 10. We're going down. We go past our 0, which is our steady state, and then we begin to come back up and converge towards that 0 again. So it will eventually converge, but it doesn't do that initially. So we get some type of oscillatory motion. So great. Thank you so much for watching this, and I really hope it helped give you a quick intro to stability and to this program here.